Okay, guys, seems to be bundled up this morning a little bit more than last week. We had a good long weekend. Any questions before we get started? Another half minute. Okay, guys, good morning. Fisher esterification, where we left off on Wednesday. Fisher esterification converted carboxylic acid to the ester. This is where we left off at, right? Okay. Okay. We're reacting an acid carboxylic acid with an alcohol. We're going to make the ester plus water. One thing is if we star this oxygen here, that oxygen there. That is, we're not going to break the RO bond. Now, this oxygen here is going to be lost as water. But actually, it could be either oxygen. Either oxygen could be lost as water. Mechanistically, paratoluene sulfonic acid, strong acid, we can use it just like we use any strong acid, H+, protonate carbonyl. We talked about why we would want to do that. Weak nucleophile that adds to carbonyl, nucleophilic addition to a protonated carbonyl gives this structure. At this point, what are we trying to accomplish? We want to essentially replace this alcohol is going to replace the water. Now note at this point, both of these OHs are equivalent. These oxygens become equivalent. Here they are. That's why I say you can lose either one. Okay, let's just say we're going to lose this one. How do you make oxygen a better leading group? Protonated. This guy's protonated because once it added, this H is here. You do proton transfer. Move the proton to this oxygen, that will give that oxygen now protonated. And over here, we just have ethyl with lone pair. I'm not doing a mechanism there because when we do proton transfer, we're not really doing a mechanism. It's probably intermolecular. H+ transfer. We've moved the proton from here to the other lone pair. The lone pair stays behind. Now the H is sitting on that lone pair. And that's a positive there. Now we have a water that we can kick off. And these electrons can come back down. Or these can come back down. Either one. You might like it better to use these over here. Let's use these electrons. These electrons come down and kick off the water. What does that give? We now have double bond to O, the H is there, that's a positive charge, and the O ethyl is there, and we kicked off what? We kicked off our water we said we were going to make. Okay, there's your product. How do we get to actual final product? Something's got to take the H. We got to get back the catalyst. Well, what gave up the catalyst? Well, the pyrotosyl O- gave it up. This can come take it back, leave the electrons behind, and we get this plus what? Plus the catalyst reform. It's an acyl substitution reaction with addition, elimination. But we have protons to take care of. We started by protonating. Then we did the addition. Then we transferred the proton. Then we did the elimination. Then we took the proton off. This is a true equilibrium reaction. That is, every step up here is reversible. Easily reversible. That is, if you had the ester, could you protonate the ester and come back to this structure? Sure, just protonate the carbonyl. And if you protonate the carbonyl, could water then add to the carbonyl electrons up? Sure, and that would give this. Then, could the proton be transferred from this oxygen to this one? Sure, why not? I mean, this is a 50-50 equilibrium. Why would the proton prefer to sit on that oxygen rather than this oxygen? They're both equally basic. And at this point, could we reform pi bond from one of these oxygens and kick off the ethanol? Sure, why not? And at this point, could you lose proton and go to neutral? Sure, why not? This is a true equilibrium reaction. In fact, in another lecture, we're going to look at the reverse reaction. But I'm not going to cover the mechanism because I'm going to refer you to this right here and say we already did it. Just do this one backwards. Okay? That is, later on, we'll say we can go from an ester to an acid. It's the same mechanism, just backwards. Okay, so how do we drive this equilibrium to product? Because this has to be driven. Well, Le Chatelet tells us that we can do this how? How would you drive this to the product? How would you drive this to the right?
Put more of the base reagent, or the original reagent.
More of what?
The carbonic acid.
More of the carboxylic acid. Is adding carboxylic acid going to drive this reaction to the right? No. No, you need to think about that. For example, at equilibrium, let's say it's 50-50. If you add more carboxylic acid, it's not going to work. Because you're always going to be left with 50% carboxylic acid. You have to think about that.
You're always going to have 50% when you add more. The one have to go down and that has to go up.
What are your two starting materials? Well, look, this is what works. If you added more carboxylic acid, you would make that one go down. But you can't make this go down by adding more of it.
I wasn't trying to go down, I was trying to equal product.
Okay, well good. You'd make more product, but you wouldn't really be driving the equilibrium.
I see.
You had to think about it. I'm glad you recognize that. Adding more of this would make that go down. You just got to be careful because, I mean, hopefully you realize you can't diminish this by adding more of it.
Right, yeah.
Okay, good. Let's just end it there. But of these two, typically this is the main one. What you can do is you can add more ethanol. These are your two starting materials. If you add more ethanol, it will push it to the right. If you consider you want to push this, then you'll be left with a lot of ethanol at the end, but that'll be okay. Because that's just solvent and that can be removed. A lot of times this reaction is done by using a large amount of ethanol, because that'll drive this over there. Another way to do it is to look at what you're making. And what would you do to these? You want to drive it this way.
Take the water, less water.
Remove water. Yes. Another way to do this is to remove water. To remove water, the equilibrium will move to the right. Water can be removed by distilling it out. Possibly. Could it be? Boiling point 80, boiling point 100. You try to distill out the water, the ethanol is going to distill out. Got to be careful. The main way of pushing this is to use excess alcohol. Okay? Because of that, you typically only do this reaction with small alcohols. So you use excess of the alcohol when the reaction is done, then you can just like rotavap off the alcohol. If you use a large molecular weight alcohol that cannot be rotavapped off, you're going to have difficulties in using excess alcohol. This has to be driven. Think about that. Fischer esterification. Most commonly done with like methanol, ethanol, very small alcohols. Common reaction of acids to make esters. We have the sheet here, yeah? So what did we just do? Acid to ester, right? So now you have something to put on that arrow there. Next reaction, acid to acid chloride, we've seen. Next reaction is actually another way to make esters, number 2. This is a reaction we actually have seen before in Organic 1. Treat this with base. What's it going to do? Base, such as maybe sodium hydroxide. All right, a variety of bases. What would hydroxide do? Deprotonate. Make the carboxylate anion. Then we throw in something like ethyl iodide. Go to a what? Go to SN2, and we can make an ethyl ester. Here, this oxygen is the same. In the Fischer esterification, there's a new oxygen in the product, because the new oxygen comes from the alcohol. So here we're doing an O-alkylation of the carboxylate anion. Same example we did in Organic 1. That's a second way to make an ester. Another reaction, acids can also be converted to anhydrides. An anhydride, as we'll see a little bit later again, is where you have an oxygen bonded to 2 carbonyls. Now these can be R groups on the end. When the R groups are different, it's called a mixed anhydride. This terminology is not important right now. We'll clarify it later. The structure should be clear as to how this reaction takes place. We can get an anhydride, very similar way. Treat this with base. Let's use a different base here. We got an acid. Let's use triethylamine. Everybody remember triethylamine? It's a tertiary amine. It is strong enough to deprotonate the carboxylic acid. And so we get our anion. Then we throw in an acid chloride. We know nucleophiles attack here, and what? Electrons up on oxygen, right? That's going going to give our nucleophile attack. We can join the carbon if you want, electrons up. The Cl there. Anything else on that carbon? Yeah, the methyl, right? It looks a little naked. I'm going to just make it like that. Okay, what next? Electrons down, kick off the chlorine, and what does that give? Gives product, yeah. There you go. I mean, that's it. If you just think mechanistically, then that's the structure you would have shown. What other chemistry would you have done? Nucleophile, addition, elimination. We don't have a proton here to deal with. Acyl substitution. That is a mixed anhydride. So that's the chemistry of carboxylic acids. As shown on this sheet here. We converted a carboxylic acid to the acid chloride, an ester, or an anhydride. There you go. We just showed how to make an anhydride. Now this is an anhydride that's not mixed. This is called a symmetrical anhydride. If the R groups are the same. We'll see that later. Now let's look at the chemistry of acid chlorides. What can you do with them? Well, you can go here, here, here. First off, how do you synthesize acid chlorides? Synthesis from carboxylic acids. We've already covered that though. That was covered in the carboxylic acid section. B, reaction of acid chlorides. This is reactions of acid chlorides. Reaction with alcohols or water, this will give esters or acids. Now with acid chlorides, there's no catalyst required. Acid chlorides are very electrophilic. They will react with pure water or pure alcohols. And you do not need an acid catalyst. We explain why these are so reactive. So, just water. Well, this is going to be your nucleophile, yeah? Boom, 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 electrons up. Nucleophilic addition to carbonyl. What do you want to do next? Majority of books will just bring this down, kick off chlorine. Let's consider doing something else though. Something that maybe looks a little bit more like should be done. That's an O minus. That's like hydroxide. That's like H3O plus. At this point, it looks like you got a base and an acid right there in the same molecule. What's probably going to take place here?
H plus transfer.
H plus transfer. That's going to act as a base. This is going to give up the H. Yes. Why don't we just do H plus transfer? What would that give? Look at that structure there. At this point, now let's bring these down and kick that off. That plus Cl minus. Now these electrons can take the H, leave those behind, and you get those two products. Question?
Do you have to do it like that, or could you have moved the electrons down, kicked off the core, and then?
You mean here?
Yeah. Like you have to do the H plus transfer, or could you have just kicked off? Like, man.
Because it seems like a long way, like
Yeah,
it's
like-
going all the way across that.
Like,
There's only like carbon between them.
Do what now?
It just seems like a long way for the proton to go all the way, like from the water basically at the bottom across the carbon and then to the, like sterically, it just seems so.
Intermolecular. So something
Uh,
else is
it's probably intermolecular.
that proton isn't actually.
I'm not showing a mechanism of this. We can go from here to here if you want. Another way to do it, H plus. We got water. That is, we can show another molecule maybe. That's another molecule the same. This can take the H, leave those behind. At the same time, this can be taking the H of another molecule. But this takes an H and something takes an H from this one. What does this molecule become? That. So it's, the H plus is not necessarily intramolecular, it's intermolecular. Multiple molecules going on here, but we can basically say something takes this proton off, but this takes a proton from something. When that happens, we get this structure. We call that just an H plus transfer. I said this chemistry, it's the same old mechanism. We'll have to do what? We'll have to deal with the proton. Well, I'm dealing with the proton right here. Does it make sense, though, if you have a structure where you have a minus and a plus internally, that they would want to maybe lead to a neutral by this? I think it makes fairly good sense. That's why I showed it. I put a question mark there. I also said that most books probably will not do it. But what do we strive for in mechanisms? We strive to show the most reasonable, logical, sound process for how a reaction may take place. I think this is pretty sound to show this. At this point, anytime you make a pi bond with a lone pair kick off a leaving group, that's pretty easy to do. That's why we did it. Reforming the carbonyl, that's a strong bonding arrangement. That's driven here. By the way, we know this is a target product. We know if you take this and treat it with water, you get this. That's the starting point. So how do we get there? You might say, well, why would this do this? Well, keep in mind, because we got to get there. That's why we're doing it. Then we produce HCl. For example, if you combine these, you can test for pH paper. It will become acidic. So, we did not have to protonate the carbonyl like we will do later on. We have to. Acid chlorides are very reactive. They react with pure water. This is why you don't find acid chlorides in nature. Because in nature, it's usually sort of wet. It rains and stuff. So acid chlorides tend to be reactive intermediates that are made in the lab. Acid chlorides are never going to be a part of a drug, because they would never survive just in the mouth or in the stomach. They're reactive intermediates. You can do the same thing with an alcohol, no acid required. You'd get the methyl ester. It's the same exact mechanism, except there's a methyl on the oxygen, and when you're done, there's a methyl on the oxygen. Now, of course, you could use a stronger nucleophile if you wanted. That doesn't mean you can't. You could react this with KOH followed by H plus workup. We've seen H plus workup before. I don't know that we clarified why. First off, this is next week. Okay, we have KOH, hydroxide. Boom, 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 electrons up. This here. There's no proton to deal with here. I mean, you could say, well, why don't I move this proton here to here? Well, that's just not going to give anything new. It's still going to be an anion. We're going to move these electrons back down, kick this off. What does that give? We'll give the OH. Is that it?
Plus ECL.
Then the hydroxide will take the proton, leave that behind. And this is in step 1. How are we going to get the neutral product?
That's the whole.
Now we bring in the H plus workup. What's your favorite acid? HCl, that'll work. I'm just going to say H plus. These electrons, and there you go.
Because it's such a strong base.
How many equivalents of KOH did we actually need?
2.
2. Why not just use one equivalent? Then we could just stop here, right?
I agree.
But you can't do that because it's such a strong base. I mean, well, I guess you could.
If you just use one equivalent of KOH, the reaction would only go 50%. Because half of it would react here. Say the reaction was going 50%, you made 50% of this and you got 50% of this left. The hydroxide will then react with the carboxylic acid. Acid-base reactions are very fast, instantaneous. You have to include enough to also deprotonate the product. In this case, we're making an acidic product under basic conditions. How is the acidic product going to exist? If you make an acidic product under basic conditions, how's the acidic product going to exist? It exists in the basic form. Many years ago, I don't know where this came from, but somehow we came up with a way to remember this. If you knit a sweater in a pool, swimming pool, on the weekend, the sweater will be wet. And thus, when you get through knitting it, it will then have to be dried. Okay? It's so stupid, it's mind-boggling. But if you knit a sweater in the pool, it's going to be wet, then you're going to have to dry it. If you make a carboxylic acid under basic conditions, it's going to be in the basic form. You're going to have to put the proton on. Okay? You cannot make an acidic product under basic conditions and say, okay, base,
Leave it alone.
don't do anything with my acid. It ain't going to listen to you. So if you want to do crocheting in the pool, you're going to have to dry your product. Okay, another reaction of acid chlorides. Reaction with amines. Ammonia, primary and secondary amines to give amides. Acid chloride, ammonia, you can get amide, plus maybe HCl if you just strictly balance it. The electrons here, electrons up. I'm just going to call that R. Nitrogen. Nucleophilic addition to carbonyl. Now you could possibly argue for a proton transfer. If you did that, that'd be fine, probably because you're going neutral. I'm not going to do that every time. Again, many of these mechanisms have nuances. What if we just bring these back down and kick off the chlorine? What does that give? Now we have the NH3. Plus Cl minus. This needs to lose an H. This can take the H. Leave that behind. What do we get? There you go. That's how you can show products. Might consider a proton transfer. One thing about doing a proton transfer, it would make this nitrogen neutral. You do have a question here. Which is a better leaving group, a neutral chlorine or a positive nitrogen? Which is a better leaving group? We know we have to clear off the chlorine, but is it a better leaving group here? What if the nitrogen was neutral? Which would be the better leaving group? Chlorine. You see, if you did a proton transfer, it'd be, the chlorine would clearly be the better leaving group. But I'm going to do it anyway here. Okay, there's a problem with this reaction. We produce HCl. It didn't matter up there. What's the problem with the HCl? Your amine. Amines are basic. If you start generating HCl, the ammonia will start wanting to go over there and react with it. You've got to take care of the HCl. You've got to quench it. Two ways to deal with the HCl. You can use two equivalents of ammonia. Then you will have a full equivalent to react as needed. The other equivalent will you just let it go over there and react with HCl. So if you use two equivalents of HCl, instead of making HCl, you will make ammonium chloride.
Question. Isn't the lone pair on the amine group not basic because it's next to a double bond for 5 electrons?
No, I didn't say the amide was basic. I said the amine was basic. So if you use two equivalents of ammonia, you would make your amide plus ammonium chloride. Okay? Now that's fine if your amine is cheap, like ammonia or maybe methylamine. Those are cheap and you can use just two equivalents. But what if your amine is expensive? You wouldn't want to waste half of your amine just to act as an HCl scavenger. In those cases, you would use some other type of amine, such as triethylamine or pyridine. And we see examples below. So show the product of the first reaction. So we have this N-methyl amide plus plus that salt that's made as a byproduct. So one equivalent of the methylamine displaced the chlorine here. The other equivalent of methylamine reacted with the HCl. Of course, this is our key product here. That'd be water soluble, water layer in an extraction or something. Okay, how about this guy down here? First off, who said when you react an amine with an acid chloride that the acid chloride has to be on the left and the amine on the arrow? Nobody. Down here we have the amine over here and the acid chloride on the left. What is triethylamine for? That's a sacrificial amine that's included to pick up the HCl that's going to be generated. So I'll show the product here. Triethylamine being a tertiary amine will not react with the acid chloride. Now that's a little white lie. It will maybe react, but it ain't going to give a product. If you want to know why, we can talk offline. But just letting you know, we don't have to worry about this reacting with the acid chloride. Or pyridine. Those are not going to give products with acid chlorides. That's where they're used to pick up the acid. Product here. Look at this acetyl group, the chlorine. There it is, under my hand, the chlorine. But no longer, because under my hand now is the nitrogen nucleophile. The nitrogen nucleophile displaced the chlorine. We lost one H, not both of them. Like we mentioned in the lab, we turned the amine into what? An amide, but what type of amide? If under my hand was an OH, that would be acetic acid. So it's an amide of acetic acid. What do we want to call that?
Acetamide.
An acetamide. Yeah. So we made an acetamide of the amide by reacting it with an acid chloride using triethylamine to scavenge the HCl. Why not just use two equivalents of the amine? Because this is not just a simple amine. This is probably much more expensive. Maybe it took you a year to make this. If it took you a year to make it, do you want to use half of it just to react with HCl? Or would you rather bring in something like this to do that job? Something that's cheap. In this case, you want to use, up here methylamine is dirt cheap. Just use two equivalents. But down here, maybe not so. Okay, acid chlorides. Let's make sure we know the difference between them and a carboxylic acid. An acid chloride is a key intermediate for doing acylation chemistry. Much better to use the acid chloride. Why not just use the carboxylic acid? If you try to react a carboxylic acid with a strong nucleophile, such as amines, or later on, like maybe Grignard reagents, what's going to happen? The nucleophile will just take the H, and you'll get the carboxylate anion. And if you make the carboxylate anion, one thing we can say about it is now this is typically unreactive towards nucleophiles. Basically, if you get this, game over. Okay? Of course, that was clarified over here. What does that say?
Least reactive species toward nucleophilic.
Least reactive pretty much being non-reactive. This guy will not do a nucleophilic acyl substitution reaction, at least not in this class. Okay? Acid chlorides, on the other hand, do not have the acidic proton. So these guys will not act as bases. They will just come in here and do your acyl chemistry. Problem with the carboxylic acid, it's got the acidic proton, and that will ruin many reactions. That's okay, because we can just convert it to this. How would you do that?
SOC.
Yeah, just convert it to the acid chloride using thionyl chloride, then react with your strong nucleophile. And you won't have any problem. So acid chlorides are a key intermediate for acylation chemistry. Also very reactive, right? Okay, anhydrides. So we can introduce them a little bit more. A symmetrical anhydride, where the groups over here are the same. By the way, this is called acetic anhydride because it's basically the anhydride that comes from acetic acid. We'll talk about how and why. Acetic acid is usually abbreviated like this. Two acetyl groups on an oxygen. Two acetyl groups on an oxygen. This is a mixed anhydride again, where the groups out here are different. I call it, many people call it mixed anhydride. Some people will call it a non-symmetrical anhydride. But mixed anhydrides are common term. Okay, how do you make anhydrides? Synthesis from carboxylic acids. By this method, which we saw earlier today, back in 2C. You've already seen that method. Second method. By the way, guys, this chemistry keeps cycling back on itself. Because we go, earlier anhydride was a product, now we're saying, well, what can you do with anhydride? And we're saying, we'll refer back to that. Okay? It's all just, organization will be a key thing here, even more than before. Another way is by thermal or chemical dehydration of a carboxylic acid. This is actually good only for making symmetrical anhydrides. For example, if you just take acetic acid and heat the bejeebies out of it, like at about 300 degrees, nice and hot, you'll get the anhydride plus water. And at 300 degrees, the water will come off as steam. Go to the lab, take acetic acid, and get it up very hot. It will start giving off steam. Now, practically, it's a little difficult because you'll also start boiling away your acetic acid. So you kind of have to do this like under pressure and stuff. There's some practical aspects. Why is this called an anhydride? You start with this, To make this, this has to lose what?
Water.
It has to lose water. So the remaining is called an anhydride. It has lost water. Okay? So that's practically where the name comes from. It's an anhydride. But we know it's an oxygen bonded to the two carbonyls. Okay? Now, mechanistically, do I discuss mechanism? How much?
Nope.
Go on next page. No. You can probably do this mechanistically. Just take two of these. And then you can take either oxygen and they'll become equivalent. And basically, we attack and we lose the water. And then this oxygen ends up bonding here. You can work through it and propose a reasonable mechanism. I'm not going to really show it. Just heat, and so we're calling it a thermal dehydration. Why does it not work in making a mixed? Why not include two different acids to maybe try to make this? Problem is because if you want these two to react together, what's keeping this from reacting with itself? To give that. Or this reacting with itself to give that. If you try to do this reaction with two different acids, you're going to get three different anhydrides. And that's just typically not useful. Not a good way. With this guy, you take this, just the same molecule, you can get the symmetrical anhydride. That's a good reaction. Now, it's also common to see cyclic diacids or diacids. If you heat these, you'll get the anhydride made. It'll be a cyclic anhydride. And the oxygen bonds to the other carbonyl and you lose water. A cyclic anhydride. This is actually a very common reaction. It actually tends to be a little bit easier than the non-cyclic. Really what we're going to say here is this being a dicarboxylic acid and this being a what? When it self-reacts? Intramolecular dehydration. These tend to be easier and a little bit more common. Did we do Diels-Alder in organic 1? I don't think we did, but sometimes we use maleic anhydride. I think we may have done it in the summer. Maleic anhydride has a double bond here. Okay. And if you look back at that lab, it says anhydrides would be introduced in organic 2. Well, here we are. Okay. Okay, reactions of anhydrides. We may be getting close to time. Let me see if there's any questions. By the way, there's it's either in the handouts or maybe in the workbook, acetic anhydride. That right there is acetic anhydride. Acetic anhydride is actually one of the biggest chemicals on the so-called black market, illegal trade market. Acetic anhydride. Anybody know why acetic anhydride is heavily trafficked on the black market?
It's a good option.
You make drugs with it.
It's used to acylate morphine to give heroin. Okay. Right? It's an acylating reagent. Okay? We're looking at the chemistry there. Okay? In some countries around the world, acetic anhydride is smuggled into and out of huge amounts. We're looking at the chemistry of anhydrides. Any questions about lab today? did some of you use acetic anhydride in lab last week?
Yeah.
Hopefully the answer is yes, because I know many of you did.